Hello, and welcome to part two of the Science for Sustainability Symposium, organized by Thermo Fisher Scientific. My name is Ray Chen, and I'm the Senior Manager of the Applications Group for the Spectroscopy business at Thermo Fisher Scientific. We are excited to have you join us today, and I would like to kick off the series with a brief commentary. So what is sustainability? Sustainability came from the word sustainable. Sustainable is an adjective for something that's capable of being continued at a certain level. Nowadays, sustainability is defined as the processes and actions through which humankind avoids the depletion of natural resources in order to keep an ecological balance that doesn't allow the quality of life of modern societies to decrease. The term sustainability has been broadly applied to characterize improvements in many areas, such as natural resources overexploitation, manufacturing operations, the linear consumption of products, technological developments of business, and general institutional changes. Here are some specific examples. Sustainable chemistry is a scientific concept that aims to improve the efficiency with which natural resources are used to meet human needs for chemical products and services. Sustainable chemistry encompasses the design, manufacture, and use of efficient, effective, safe, and more environmentally benign chemical products and processes. Sustainable chemistry is also a process that stimulates innovation across all sectors to design and discover new chemicals and production processes that will provide increased performance and increased value while meeting the goals of protecting and enhancing human health and the environment. Another example, sustainable manufacturing. Sustainable manufacturing is the creation of manufactured products through economically sound processes that minimize negative environmental impact while conserving energy and natural resources. Here's another example, sustainable energy. Sustainable energy is one that is able to meet the growing demand of today's people without compromising the demand in the future. All renewable energy sources like solar, wind, geothermal, hydropower are forms of sustainable energy. Renewable energy sources have a low environmental impact, widely available, and are naturally replenishable. So this is today's program. Bioplastics are biodegradable material that come from renewable sources. The advantage of bioplastics include to reduce carbon footprint, provide energy savings in production. They do not involve the consumption of non-renewable raw materials. Their production reduces non-biodegradable waste that contaminates the environment. It is an exciting research field that's expected to grow continuously. Today's program focuses on bioplastics, and we have 4 excellent talks lined up for you that touch different aspects of bioplastics. Tomorrow's program is slightly more diverse, but still centers around the overarching theme of sustainability. We have 2 talks on plastic recycling, followed by some fascinating research projects on green chemistry, renewable energy, and additive manufacturing. I want to take this opportunity to thank all our speakers for the generous donation of their time to make this symposium possible. So being a leader in serving science, we are excited that some of our technology and instruments are an integral part of these research projects. But more importantly, being the citizens of the planet, we take pride in enabling our customers, these scientists, to advance their research for a cleaner, safer, and a healthier world. So I want to spend the next couple of minutes to talk about some minor logistics. As you walk in, you see the lobby, and if you need any help at any time, please click on that little box say chat with a rep. One of us will get in touch with you. At the bottom of this lobby, you see some small icons. Click on the icon. Biomaterial and recycling will take you to the atrium. When you walk into this atrium, you see 2 banners here. So you click on Watch Now, that little box there will take you to the studio. a pop-up window will show up, which has a list of today's program. Just keep in mind, all these presentations, they are on schedule and on demand as well. So if for any reason you miss, any of the talks, you can always come back to view those talks on demand. Now, while you listen to or watch this presentation, if you have any questions, there's a little box says Q&A. Type in your questions. We'll collect that information and get back to you. The last thing I want to mention here is the briefcase. In the lobby at the bottom, you see that little icon says briefcase. In that briefcase, we put a collection of marketing collateral, product information, publications, application notes, and I hope you can find those information useful. I want to conclude my comments or remarks with this slide. As scientists, we ought to ask ourselves this question for us and for our children. What does sustainability mean to you? Enjoy the program and take care.
Welcome, ladies and gentlemen. It is my pleasure to introduce to you Christoph Hess. Christoph is a professor for non-metallic materials with the Faculty for Technology and Bionics at the Rhine-Waal University of Applied Sciences here in Germany. His research focus, and this would also be the topic of his talk today, is on biopolymers, polymer recycling, and self-reinforced polymers. Christoph got his PhD in physical chemistry at the University of Osnabrück on gel structures based on renewable raw materials. Prior joining the university, Christoph's expertise spans across a wide field of sustainability sciences. He worked on process and environmental engineering for groundwater and soil vapor remediation. For over 10 years, Christoph was an industrial research manager for the compounding of biopolymers. So with this, I would like to hand over to Professor Hess for his presentation.
And in this presentation, we will talk about bioplastics. I will give you a brief introduction where we first talk in general about plastics, global plastics production. Then we need to distinguish between bio-based and biodegradable plastics. Coming from there, we can define a bioplastic because that is a vital source of misunderstanding even today. A short look at the production of bioplastics. Then we have a look at the base polymers that are used for bioplastics. And very important, disposal, organic recycling, composting of bioplastics, and finally, the bio-based carbon share as a parameter to assess the renewable share of a bioplastic. So if you first have a look at the global plastics production over the last around 70 years, we can see a steep increase of plastics production, starting out in the late 1950s and an exponential increase ongoing today of global plastics production. We have a look, there are only two short periods of declining quantities. We can see here that is the mid-70s, that is the oil crisis, and here at around 2008, the global economic crisis, but all the rest is steeply increasing to around 400 million tons in 2015. That was the wrong direction. Now, if we have a look on how the different industrial sectors contribute to these 400 million tons in 2015, then we can see that the vast majority of plastic production is used for packaging, around 146 million tons. So the quantity of packaging alone equals the quantities of building and construction, textiles and consumer and institutional products put together. So the vast majority of plastics production that goes into packaging. And the question is, where do these raw materials come from to produce that huge amount of plastics? Almost all plastics today are made of fossil resources, such as crude oil. That is the raw material base. If we have a look at this slide here, we see the crude oil distillation, the fractional distillation, and only one fraction of this crude oil which is the naphtha fraction. That is the most important fraction for the production later of polymers, and from there the plastic materials. So we have the other well-known fractions like heavy diesel, light diesel, kerosene, but most important for chemical substances, raw materials and monomers for polymers and plastics, that is the naphtha fraction. And as we all know, this crude oil, that is a fossil resource and that is limited. That is a limited resource, and this limitation that is indicated by the so-called peak oil. The peak oil that shows the maximum production of oil, maximum amount of oil that is produced a certain year, and from there on the quantity will decrease further. So the peak oil, that is the year of maximum crude oil production. And this peak oil, that is usually shifting more and more towards later years because we have new exploration technologies that are available. For example, think of fracking. So with new technologies, we can exploit new resources of crude oil. But at the end of the day, for sure is crude oil is limited. So the peak oil will be shifted to later years, but one day peak oil will be reached and then produced quantity of oil will decrease. And for that reason, bearing in mind that we have a limited resource for the production of plastic materials, we are looking for alternatives. And some of the raw materials for the production of polymers, they can be made from annually renewable bio-based sources. So that is not limited, but renewable. And any share of such bio-based renewable source will help to save the fossil resources that are still available. So a first definition of bioplastics is that bioplastics are polymer-based materials that are at least partly made of renewable organic resources. At least partly. Now the problem is, what will be the minimum share renewable resource to be able to claim a plastic to be a bioplastic? That is not really defined, but different certification bodies have different approaches to define this minimum share. We will see later, some of them, they say we need at least minimum 20% of renewable resource, and then we are allowed to call the plastic a bioplastic. But again, any share of bio-renewable resource helps to save the fossil oil resources. Now, if we talk about renewable resource, we need agricultural land to grow these resources. There is a vital discussion about land use for materials instead of food production. But usually we say we should use our land for food production and not for the production of materials. And that discussion, you will know, that has started with the introduction of biofuels that time. This food versus fuel discussion. And that is ongoing also if it comes to the production of raw materials for bioplastics. Here on this slide, we see the land use for different applications. And we start with the global land area, that is the big circle here. The global land area, that is around 13 billion hectares, that is 100%. Then 37% of this global land area, that is agricultural area. Now we can further split this area, and now we see that more than 2/3 of this global agricultural area, that is used for pasture. But remember, the meat production that requires a huge amount of pasture. That is the vast majority of the global agricultural area. Then if we go here down the list, we see the material use, the area that is used for materials, that is just around 2% of the global agricultural area, and for biofuels around 1%. And if we further split the material use sector and choose and select the bioplastics, you see that is almost neglectable. That is 0.016% of the global agricultural area, and estimation for 2024 is around 0.02%. So that is an almost negligible share of agricultural area that is required for the production of bioplastics. So that was one approach for the definition of bioplastics if we come from the raw material side. If we go and move to the opposite side, from the side of disposal of material, we can create another definition for bioplastics. And to illustrate that, we have a look first here at the municipal waste treatment, this example of the European Union over the last 25 years. And here we can see a trend away from landfill. Landfill, that is the green area here. You can see that is going more and more narrow, that sector. So we have a trend away from landfill towards material recycling, here in blue, incineration, red, and composting, again in blue. The reason for that is that the landfill capacities in many countries, they are exhausted. And for that reason, we need to reduce the volume of waste. Volume reduction of waste, that can be done, for example, by incineration or by composting. And of course, by material recycling, if we can reuse the material instead of disposing it immediately. So here composting is one option to reduce the volume of waste. Of course, landfilling in many countries is no longer possible. For example, in Germany, it's no longer allowed. Landfills are completely exhausted here. Now, if we have a biodegradable, compostable plastic, then it is very important to know that in industrial composting plants, partly biodegradable plastics would create problems. Because at the end of the composting cycle, the persistent share will remain. All have heard about these microplastic particles. So the persistent organic material will remain in the compost fraction, and that has to be sorted out if it's still visible. And for that reason, only fully biodegradable plastics are suitable for composting and should be assigned to the group of bioplastics. That is different to the definition we have seen before, where we had defined a share of bio-based raw material that could be below 100%. But if it comes to biodegradation, we need a fully, completely biodegradation for a plastic if we want to use it as a compostable bioplastics. So a second definition for bioplastics, that is a polymer-based material with completely biodegradable organic share. Partly biodegradable, that does not make sense. On this image, one example, there is a compost contamination. See here this plastic bag and other persistent fractions, and that has to be sorted out. For that reason, the biodegradable plastics have a very low acceptance by the composting plant operators. Because if there is some incorrect sorting, have this contamination of plastic in the compost, and that has to be sorted out. So the operators very often say, we do not want the biodegradable plastics because people do not know and they are not able to distinguish. And then we have the persistent plastics also in the compost fraction, and that is not desired and creates a lot of trouble and effort. The decomposition rate of persistent non-biodegradable plastics that leads to severe pollution. One example, very well known, that is marine littering. Here are some examples for the decomposition rates of marine debris items. And the bars in blue, they indicate plastic products. For example, fishing lines, plastic bottles. You can see decomposition rate 450 years. Also well known, the plastic beverage holder, the 6-ring, 400 years for decomposition. Or a cigarette butt, we will see later, 5 years. So that creates a huge problem with pollution if we have a non-appropriate waste management. That is very important to point out that this includes also the biodegradable plastics. So an appropriate waste management is key for fixing the littering problem. Even a biodegradable material should not be used for uncontrolled littering, because that would undermine the awareness of proper waste management. That is a very important point. So biodegradable, compostable plastics will not solve and fix the littering problem. The waste treatment has to be appropriate and well ordered for any plastic, whether it's a conventional plastic or a bioplastic. Now, if we put together our two definitions for bioplastics, we can create a general definition. Bioplastics are fully or partly synthetic macromolecular materials that are based on biogenic renewable raw material, for example, biopolymers, and or are biodegradable. And this and or, that means that we also have fossil crude oil-based polymers, plastics, that are biodegradable. On the other hand side, there are also bio-based but non-biodegradable plastics existing. That classification that is shown on this slide here. So we have four groups of plastics. See here this cross line. So we have the line for bio-based, and we have the line for biodegradable, non-biodegradable. So all materials here to the left are non-biodegradable, and all the materials to the right here are biodegradable. Upper half, we have the bio-based materials, and in the lower half, we have the fossil-based materials. So here, bottom left, that is the group of conventional plastics that we know, the crude oil, conventional plastics, non-biodegradable, like conventional polyethylene, polypropylene, or PET, polyethylene terephthalate, that is used for beverage bottles, for example. Now, if we go upwards, we have bio-based, but still non-biodegradable plastics. These are the so-called drop-in bioplastics. That is, for example, bio-based polyethylene, PET, polyamide, or PTT, that is polytrimethylene terephthalate, that is used for textile industry, for example. So these are bio-based polymers, but they are not biodegradable. So a bio-based polyethylene, that is polyethylene, and chemically we cannot distinguish between this polyethylene and the conventional polyethylene. The chemical behavior is exactly the same, but the raw material source here, that is bio-based. Now if we go to the right, we have the bioplastics that are bio-based and biodegradable. This is, for example, polylactic acid, polyhydroxyalkanoates, polybutylene succinate, or some starch blends. So these are bioplastics that are bio-based as well as biodegradable. Then here, bottom right, we have biodegradable polymers, plastics that are crude oil-based. For example, PBAT, that is polybutylene adipate terephthalate, that is an aliphatic aromatic copolyester. We will see in a minute the structure, or for example, polycaprolactone. So these usually crude oil-based polymers are biodegradable. We have to be aware that we have these four groups of plastics, and only three of those, bio-based and or biodegradable, are put in the group of bioplastics. So we have three groups of bioplastics and one group of non-bioplastics of conventional plastics. Now, if we have a look at the production capacity for these bioplastics, that is shown here on this slide, distinguish again here with bio-based non-biodegradable portion here to the left, and the biodegradable plastics here to the right. Then we see we have many different polymers, but the majority, that is here bio-based polyethylene, bio-based amide and PET. Also, again, from the textile industry, PTT. To the right, PBAT is widely used, but of course also well-known polylactic acid and starch blends. Pure starch is not a thermoplastic, so starch usually is used together with other thermoplastic polymers in so-called starch blends, and they are widely used, for example, for flexible packaging. In 2020, that sums up to around 2 million tons. We compare 400 million tons in 2015 for the global plastics production. That is only a very small portion, but it's increasing slowly but steadily. And again, if we have a look at the market segments where these bioplastics are used, we have a similar picture that we have already seen for the global plastics production and market segments, because here again, the majority of bioplastics is used for packaging, whether it's rigid packaging or flexible packaging. Biodegradables, predominant in the flexible packaging, example in compostable refuse or shopper bags, widely used, and here in rigid packaging, for example, PET, bottles, and other materials. Again, mentioned before, the polytrimethylene terephthalate, PTT, here highlighted in blue, that is widely used in the textile industry. It's also interesting here in the agricultural sector, we have a big portion here, PET, that comes from this biodegradable, compostable mulch films, these agricultural films. But again, similar to the overall market of plastics, also the bioplastics are widely used or predominantly used in packaging application. Now we can use different groups of raw materials and polymers for the manufacture of bioplastics. Of course, we can use natural biogenic polymers. I have already mentioned starch, but also cellulose, chitin, chitosan, or PHAs, the polyhydroxyalkanoates. So that is natural polymers, also called biopolymers. That is one source of raw materials for bioplastics. The advantage here is that the polymerization step, that is done by nature. So these molecules are already polymers. They are made by nature, natural polymers. But if the properties are not suitable of these natural polymers, we can also modify these biogenic polymers. Usually that is a chemical modification. For example, the cellulose can be converted to cellulose ester. We'll see an example later for a cellulose ester. So we have modified natural polymers also as a raw material space. And again here, the polymerization step has already been done by nature. So we use readily made polymers and we just modify these polymers. Different to that, we can fully synthesize bio-based polymers. So we start here from monomers, but we can use bio-based monomers. These materials are used for these bio-based but non-biodegradable drop-in plastics like biopolyethylene or bio-PET. And finally, we can also use crude oil as a raw material base for the fossil-based but biodegradable polymers. As mentioned, an example is PBAT. So we have different sources of raw materials that can be used for the manufacture of bioplastics. Here, as already mentioned, an example for a modified biogenic polymer that you all know, that is the cellulose acetate. To the left, we can see the repeating unit, the molecular structure. So we have glucose units, come from the cellulose. And attached to that glucose units, we have acetate groups. They are not present in the natural cellulose. They have been attached by chemical modification. This cellulose acetate that is widely used, for example, for the manufacture of cigarette filter material. Almost all cigarette filters around the world are made of cellulose acetate. Here, as you can read at the bottom, we have to bear in mind that this chemical modification, depending on its extent, that can impede the biodegradability of the polymer. So everybody will agree that a natural cellulose, cotton, that is biodegradable, completely biodegradable. But if we chemically modify this cellulose to a certain extent, that can lead to a decreasing biodegradability, or sometimes even can fully inhibit the biodegradability of the molecule. Which means that the cellulose acetate will no longer be biodegradable if we have too many of these acetate groups attached along the chain. This is something we have to bear in mind if we chemically modify biopolymers. Other example, as I've mentioned before, quite complex, that is this PBAT, polybutylene adipate co-terephthalate. That is an aliphatic aromatic copolyester. So here we have an aromatic acid to the left, that is terephthalic acid. Then we have an alcohol here, that is butane diol. Then we have an aliphatic acid, that is adipic acid. And again, we have a butane diol. Aromatic acid, aliphatic acid, two alcohol groups, and they together form the repeating unit of this polyester. This M and N here, that indicates that sometimes we have different number aromatic and aliphatic repeating units. But this entire molecule, this polymer, this PBAT, that is completely biodegradable. But initially completely made from crude oil. That is a fossil-based biodegradable polymer. Now the question is, how can we certify the compostability of a material? Because we want to label these products. We want to be able to see whether a plastic is compostable or not. There is one example for a standard that I want to show here. That is the European standard EN 13432 that deals with industrial composting. There are different requirements for the material to fulfill this norm, this standard. For example, within 90 days, fragmentation needs to happen. And the biodegradation, which means the conversion of the material into carbon dioxide, water and biomass, that should be finished and complete within 180 days, which is roughly half year. Furthermore, during composting, no toxic substances should be. During composting, no toxic substances must be released to the environment, to the compost. So we need an ecotoxically harmless material. Also, no heavy metals should be released from the material to the surrounding compost. So composting according to the European standard EN 13432, that does not just mean that we have a bioconversion of the plastic and it will disappear, but also we have the requirement of harmlessness. That is very important because the quality of the compost should not be affected by the compostable plastic. If all requirements are fulfilled, then the product can be certified and would be labeled, for example, with this logo, that is a seedling. Certco is now labeled to be compostable. What is also quite important is the fact that the biodegradation must be finished within a certain period of time. So if the biodegradation takes too long time, even if it happens, but if it takes too long time, then the material might not meet the European standard EN 13432 for composting. The reason for that is that in industrial composting sites, we have composting cycle time. Operators expect the material to be completely converted within this composting cycle. That takes too long. We have fractions and particles of plastic left in the compost that we then again need to sort out. This slide we see an example for a compostable product that is a coffee capsule. You can see here to the left. This coffee capsule machines, compostable capsule. At start it looks like this, and after 3 weeks of composting we can see already a fragmentation. There's some contamination with soil, with compost, but the coffee capsule falls apart in smaller particles, and after another, let's say 8 or 10 weeks time, it will completely disappeared and biodegraded. Here to the right we see some other labels, some certification labels from other certification bodies like Vinsot. They have introduced this OK Compost logo. Today that has been taken over by the TÜV Austria, but Vinsot was the body that has introduced this logo. Then, for example, from the DIN, from the German certification body, also apply for the garden compostable logo. So that is different to industrial composting. Of course, in your garden compost, we have lower temperatures. So composting there in your garden, that is more difficult. And not all materials that are compostable in an industrial composting site with the hot temperatures will automatically be also compostable in your garden compost. So for that, we have a separate additional logo. We also have to talk about another degradation issue that creates heavy discussions for many years now, and that is the catalytic degradation of plastics. So we have, for example, so-called oxo-degradable plastics, and there are suppliers that claim these materials to be also biodegradable. Sometimes they combine and say this is bio-oxo-degradables. But that is not the same as a conventional biodegradation according to the norm and standard EN 13432. Because what they do, they put catalyst material in a conventional plastic like polyethylene, and that starts to degrade by oxidation. So that accelerates oxidation of the polymer, so the plastic will fall apart in very small fractions, sometimes almost invisible fractions. But that not necessarily means that there is also biodegradation. So in biodegradation, only small conversion rates are achieved. Furthermore, these metal salts, initially that was, for example, cobalt-based catalysts, they may affect the quality of the compost by contamination of the compost. But these materials are also in the market. Here to the right, you can see logo, one of these products, and that claims this bag is 100% degradable. No, we do not know what that means. Do not say biodegradable, they just say that it's degradable. And then the misunderstanding starts. So we have to be very precise here with biodegradable, compostable, and maybe oxo-degradable materials. Another approach, that is enzyme catalytic degradation, where we put into the plastic material specific enzymes that start degradation. But on this technology, there is only limited reliable data yet, so they are also not considered to be bioplastics yet. That is still under investigation, but these materials are also in the market today. That is completely different to the conventional biodegradation. So that was the certification for the biodegradation or composting. Now, if we want to certify the bio-based share of material, then we use another approach, and that is the radiocarbon dating principle, and refers to the carbon in the material. And the principle of the radiocarbon dating, that is shown on this slide. So if we have living species, for example, this tree here, that tree takes up carbon dioxide from the atmosphere. And due to cosmic radiation, a very small portion of this carbon in the atmosphere, that comes from nitrogen. So nitrogen in the atmosphere, 14, is converted to an carbon-14 isotope. And this carbon-14 isotope is incorporated in a carbon dioxide molecule that is absorbed by, for example, a tree. You know that usually carbon has mass number 12, but not 14. So that is an isotope of carbon. And the oxygen is released to the atmosphere again, and the carbon-14 remains in the tree. Share carbon-14 in the living species, that is stable, because it's defined rate of nitrogen that is converted to the carbon-14 isotope. So the share of carbon-14 in the living tree will remain stable. In the dead tree, no more carbon dioxide can be absorbed. So the dead tree will not incorporate carbon dioxide anymore. And that means that the carbon-14 that is in the tree structure in the course of time will fall apart again by radioactive decay from carbon-14 to nitrogen-14. Half-life of this decay, that is 5,730 years. So the share of carbon-14 in dead matter will decrease over the years. And that means that in fossil resources like crude oil has been, though the surface for millions of years, all carbon-14 has converted back to nitrogen-14. So we do not find carbon-14 in crude oil anymore. That is now the parameter to define whether a material is bio-based or not, because a renewable organic resource, it's very fresh, that still has carbon-14 share present in its structure. So the carbon-14 share that is used to decide whether a material is bio-based or not. Some bioplastics, they are just partly bio-based, and to calculate the bio-based carbon share, we need to check the number of carbon in the molecule, in the repeating unit of the polymer, see whether this is bio-based or fossil carbon. As an example, I have chosen again the PBAT that we have already seen before, because there are suppliers of PBAT that offer a partly biodegradable polymer, partly bio-based polymer, sorry. And in this case, the butanediol, so the alcohol of the polymer of the repeating unit, the butanediol is bio-based, whereas the terephthalic organic acid and the adipic acid, fattic acid, are still crude oil based. Now, if we check and analyze for the bio-based carbon share, we need to count the bio-based carbon in the repeating unit, which is 8, 4 carbon here and 4 carbon here to the right in both butanediol molecules. And then we have another 14 carbons that are fossil based, coming from terephthalic acid and adipic acid. Together 14 carbon atoms per repeating unit. Precondition that M is equal to N, so that we have same number of organic and aliphatic acid molecules in the polymer structure. So in total we have 8 plus 14, which is 22 carbon atoms in the entire repeating unit, of which 8 are bio-based. And now we can calculate the bio-based carbon share, which is defined as the number of bio-based carbon over the total number of carbon times 100%. That here sums up to 36.36%. So slightly more than 1/3 of this partly bio-based PBAT is really bio-based. Refer to the carbon, because we can measure radioactive decay and the carbon-14 share in this material. Similar to the biodegradation and composting, and that is the final slide, we can certify these materials, these bioplastics, according to their bio-based carbon share. Standard is an American standard, ASTM 6866, that is widely used. And again, we have, for example, a SOT as certification body. Today that is done by TÜV Austria. But SOT, they have introduced this system, call it OK Biobased, so not OK Compostable, but OK Biobased. And then they provide 1, 2, 3, or 4 stars to the material. So for 20 to 40% bio-based carbon, 1 star, between 40 and 60%, 2 stars, 60 to 80%, 3 stars, and more than 80% bio-based carbon, that we have the 4-star bio-based label that we can ask for, and we can certify our material. Also, DIN is offering a system. They have their own system, and you can see that is slightly different from the shares. We have bio-based 20 to 50, 50 to 85, and more than 85%. But all in all these certifications, they assess the carbon, the bio-based carbon share of the material to indicate the renewable portion in the plastic, in the polymer. I hope you enjoyed this quick ride through some important aspects on bioplastics, which are an increasingly valued group of materials. But again, the bioplastics alone will not fix the littering problem. Just offer an additional option for disposal and help to save limited raw materials and fossil materials. Thank you very much for your patience and for your attention.